Hello everyone, welcome to Andy's Side Dream. Today we're going to talk about the Euler's formula and the ways of proving it. So, there are three most commonly known ways of proving the Euler's formula. First is using the Taylor series. Second way is to take the derivative of both sides. And the third way is to use integral. And today I'm going to demonstrate how to use Taylor series to prove that Euler's formula is true. And this formula is also known as the most beautiful mathematical formula in this world. And why is it beautiful? Let's take a look. So here, I've got the Euler's formula written out for you guys. And now, if we plug in pi for x, what would this equation be? So this is what it will become, right? And from our previous knowledge, we can know that cosine pi, this is basically -1 plus 0. And then if we rewrite this formula, it will become +1 equals to 0. And this is known as the Euler's identity. It is the most beautiful mathematical formula in this world. Why? Because it has the base of natural log, e, in it, and also imaginary number I, also pi in it, and also 1. I'm not sure 1 is that important, but I'm sure that they must have a good reason for that. And also 0 in it. So with those 5 components, this made up the most beautiful mathematical equation. And then let's take a look at the ways of proving the Euler's formula. So I've already got the Taylor series written out for you guys. And now why don't we just start to plug in some values. But first, before we do that, let's figure out what would the Taylor series be for e to the x power. So if we take a look at the Taylor series, this is when x equals to 0. So if we take a look at the Taylor series, the first term is just f of x. So the first term will basically become 1 plus derivative of e of x. This is also 1. 1 over 1 is still 1, right? And then, so basically 1, x minus 0, plus second derivative, still e of x, 1 over 2 factorial, x minus 0, second square. And then third derivative, still 1 over 3 factorial. So this is basically the Taylor series for e of x, e to the x power. And now, let's take a look at the Taylor series of cosine of x and sine of x. But first, let's do cosine. And for the sake of time, I've already got the cosine written out for you guys. So it will be 1 minus x squared to the 2 factorial plus. So this will be the Taylor series for cosine. And now let's do sine. Okay, so we've already got our cosine and sine function right here. And now notice that for the cosine function, because it is even, that's why we only have the even power. And for the sine function, because sine is odd, so we only have the odd power to it. And now, if we start to plug in some values, we can see that those three formulas are actually very similar. So, first, let's take a look at the e to the x power. So let's take a look at this formula. If we plug in ix for this formula, what would that become? Well, let's take a look. So the first term will still be 1, and then plus the second term, this is x, right? So it will be ix. And then the third term, this is basically ix squared over 2 factorial. And then plus, this is ix cubed, 3 factorial. Okay, so after we plug in those, this will become the new equation. And then, if we start to, I missed a plus sign over here. And then, if we know some of our identity, the imaginary number identity, then we can actually simplify this equation. Okay, so let me do the simplification work right here. First term will still be 1. Second term will still be ix. There isn't really much we can do about that. And then, but the third term, I to the second power, that's basically -1, right? So it's minus 2 factorial. Third, that's negative I. So this is what will you become. Now, plus x to the 4 factorial, plus x to the 5 factorial. Okay, so this is the work after we simplify the entire equation. And now, if we regroup this equation, things will start to become more clear. So, if we group all the terms that does not contain I in it, so it will be all those even terms. And then plus, and then the rest of the terms that does contain I in it. So it will be those terms. But notice that they all have I in it, so we can basically just pull I out. And then we can write the rest of them in it. Okay, so this will basically be the regrouped, simplified equation. And now if we take a close look, then we can actually start to see that, wait, hold on. Doesn't this part look like the cosine equation? And this part, isn't it the same with sine? So this will be cosine, and this will be sine. And now, since we have this I over here, we pull I out, I will just come down to the bottom. And now, we have already finished proving that the Euler's formula, e to the ix power, is equal to cosine x plus I to the sine x. And now, this is basically the way to prove that the Euler's formula, it's true, left and right, they equal to each other, using the Taylor series.